Hi guys, let's try to understand today's class Wheatstone's bridge. So this is one of the application of the Kirchhoff laws. So this Wheatstone's bridge, it's an arrangement of four resistance. It is used to determine one of the resistance value very quickly and accurately in terms of remaining three resistances. So if you clearly notice, this arrangement contains four resistance P, Q, R, S, and they are connected such a way like that through a cell of EMF E. The main application of this, if to find the unknown resistance, by using known resistance. Suppose if you find the resistance of here it equal to R. So R is unknown resistance. I don't know what is the resistance value. It's just like a small resistor which is having certain ohms. But to find unknown resistance, if I have known resistance values, if I have, let's say, P equal to Q equal to S equal to, I am having three known resistance. Let me take 1 mega ohm resistance value. If I know these three, which is known resistance, by using these three known resistance, I can able to find R in the circuit, which is unknown resistance, with the help of like this bridge connection, which is suggested by British physicist Sir Charles F. Wheatstone in 1843. So this is very helpful to find the unknown resistance value by using known resistance, and it will be one of the applications of Kirchhoff laws, because so in the circuits we need to apply the Kirchhoff loop rules to find the expressions. And today's class we will learn how these known resistance values will help to find unknown resistance value. So before going ahead, I would like to make you understand one more term. So that's about a galvanometer. So in our previous knowledge, we know about voltmeter. So this is what we are seeing, the big one. So this is a DC voltmeter, which used to measure the potential difference. So this is a line. So this represents it is a DC voltmeter. Now this is used to measure the potential difference across any component, and we know from lower class knowledge, we know about the ammeter also. So ammeter measures the current value in the given component, in the given circuit. So this is the DC ammeter, this is also DC ammeter. So it measures the amount of current. A part of these two, voltmeter and ammeter. So we will use one more meter. Its name is galvanometer. So galvanometer is something, it's used to identify the presence of current in the given circuit. So unlike voltmeter and the ammeter, galvanometer is used to find the presence of current or to find the direction of current. So that is also, it is noticeable with the help of galvanometer. So voltmeter measures potential difference, ammeter measures current, it measures, we can get certain values. But galvanometer, it shows, it deflects when the presence of current is in the given circuit. And this meter is also made up of certain wires and all. So usually this meter is also having its own resistance. So this meter to work, so here it is showing that its meter is also having its own resistance. So that we represent as galvanometer resistance. Okay, it means when current is passes through this galvanometer, when current, if you can connect this to a cell, so when current is passes through galvanometer, so just like how resistance opposes current, so galvanometer also opposes, because it's also made up of certain coils. Okay, so this galvanometer we will use in this Wheatstone's bridge network. So it is very good if we dealt all this in the lab and all, but for time being, if I make you to understand the galvanometer functions, so I can able to use this in the given concept. So here galvanometer is an instrument, it used to determine the presence of current in the given circuit. So to this Wheatstone's bridge, that galvanometer is needed component. So when it comes to circuit connection, so the Wheatstone's bridge contains PQRS. So these are PQRS are the resistors. For timing, you can consider that as PQRS. Those are the resistance. It's having its own resistance value, and they are connected as the 4 arms in the Wheatstone's bridge. And in the middle arm from the B to D, right at here, we need to connect a galvanometer. G here represents galvanometer. And the current which is flowing through galvanometer is represented as IG. And another end at the A and C are connected to an voltage source which is having potential difference as V. Now here let's see how current is dividing. So if I is the current is passing from potential source to A branch, A end, at A this I current is divides as from A to B, it is dividing as I1, and A to D it is dividing as I2. So A is a junction, so we apply the Kirchhoff current rule. At junction current divides. So from A to B arm I1 current is flowing, and A to D arm I2 current is flowing. And again at B is here, it is one more junction. The B is here one more junction. Now B at here again the current divides. I1 is current is entering towards to the junction B, and from the junction the current which is flowing through galvanometer, that is IG, is current. And the remaining current, if I subtract I1 minus IG, which is remain, so that current is flowing through arm B to C. That is the current which is divided after dividing at junction B. Similarly at junction D, now I2 current is entering to junction D, and IG current is also entering to junction D. Now, at this junction, these two currents are add up, and the adding currents are IG plus I2. They are passing through the arm DC. Now finally at C, the currents which are coming I1 minus IG, and the currents which is coming from the DC arm, it is plus IG plus I2. So that is the total current at junction C. Now if you combine this, Ig gets cancels, so the remaining current I1 plus I2, so which is nothing but I itself. So the division of currents are very crucial to write the expressions in the given arms. So how much current is entered at junction A, so that much amount of current is came back, it is divided at junction C. So it's better I write these equations for your understanding. I1 minus Ig plus Ig plus I2. So these two terms gets cancelled, you will end up there at I1 plus I2, which equal to I. So that is the amount of current at C. And at A, current I equal to I1 plus I2. Now this is the division of currents. Now let's apply Kirchhoff rules to the loop A, B, D, A. To loop A, B, D, A. Now if you travel in the loop in this particular direction, suppose if I draw that as a loop at here, so I wish I would like to travel in the loop in this direction, clockwise direction. If you start from at P resistance, the current in the resistance and my direction, they both are same, so we take that as, when current direction and my direction they both are same, then we take that as positive. And when it comes to galvanometer, so you remember that the galvanometer is also having resistance, so we need to consider that resistance value also. Here galvanometer, we did not represent that as a resistor, but galvanometer is an instrument, it's also having resistance, so we need to represent that as galvanometer resistance as G. So that change please notice at here. Here G is also I am taking as a resistor. So G is also a resistor. Note, I can mention it here. G is taken as resistor. So because G is a galvanometer, galvanometer contains resistance. Here we cannot draw as a resistance symbol because it's not a resistor. Galvanometer is an instrument. So that instrument we represent that as symbol, but it's having resistance. We should consider that. So when we consider the loop rule at here, the current in the galvanometer and my direction in the loop, they both are same. So again here we need to consider that as a negative. When it comes to at resistance R, current direction and my direction in the loop are opposite. So here we need to consider that as positive. So if I write the loop expressions to the loop A, B, D, A, to loop A, B, D, A, so I can write that minus I1 times P and minus Ig. First I write the Ig is galvanometer current, Ig times G, here G is galvanometer resistance, and plus I2 times R, so that is I2 is current in the arm AD and R is resistance, which is equal to 0. And if I rewrite these expressions, so I will take it out negative, so I1P plus Ig times G minus I2 times R, which is equal to 0. Let me take this as equation 1. So that is the expressions which I get from ABDA. Now suppose if I apply the same Kirchhoff loop rule to the loop BCDB. So in this loop, now to the second case, we need to apply the Kirchhoff to the loop BCDB. So this time also I would like to walk in the loop along the clockwise direction. So when it comes to across resistance Q, the current direction and my direction in the loop, they both are same. So we take that as negative. So that I can write that negative minus, so minus that is I1 minus Ig times the resistance value is Q, I1 minus Ig times Q. And when it comes to resistance S, current direction through resistor and my direction in the loop, they both are opposite. When they both are opposite, we take that as positive. So there I get it as plus Ig plus I2 times S. Now when it comes to galvanometer resistance, so my direction in the loop and galvanometer current, again they both are opposite, so I can get that as positive value. So plus Ig times G, which equal to 0. So if we rewrite this expression, I would like to remove minus from the first expression, so this expression will be changed as I1 minus Ig times Q minus Ig plus I2 times S minus Ig times G equal to 0, at equation 2. Nothing we did, just take it out the minus from the first expression. Now these are the two expressions. So here I am using a special case that is called, it's very important, when the bridge is balanced. When the bridge is balanced. So what is the meaning of this sentence at here? When the bridge is balanced, it means usually if you use resistance as a practical purpose in the Wheatstone's bridge and all, so during at a particular situation, if you use the resistance PQRS, so here I started with the three known resistance means three resistance values I already know it, and I need to find the unknown resistance. So if I know the three known resistance, means I already know what is the resistance value of the three which I already used it here. And by using that, I need to find the unknown resistance with the help of the galvanometer. So when bridge is balanced, so when that situation comes, so the current through galvanometer becomes 0. So the current through galvanometer becomes 0. Now this is the condition we need to get it by using the three resistors. So how the galvanometer current goes to 0? So that we will understand by writing mathematical expressions. So for a moment you can consider this as a statement. When the bridge is balanced, then current through galvanometer equal to 0. So by that case, how the equation 1 changes? Now equation 1 changes as So when ig equal to 0, now I can write that I1p plus ig equal to 0 times of g minus I2 times r equal to 0. So this will turn simple expression I1p minus I2p equal to 0. Let me equation 3. And likely how the equation 2 changes in the balanced condition. So equation 2 changes as so in the place of ig I can substitute 0. So therefore I1 minus 0 times q minus of 0 plus I2 times s minus 0 times g equal to 0. Now this expression will change like I1 times q minus I2 times s, which equal to 0. Let me consider this equation of 4. Now this equation 3 and 4, suppose this is r, sorry, so that is r. So equation 3 we can also express that as I1p which equal to I2 times r. Okay, and equation 4, this I can write as I1q which equal to I2 times s. Now if we divide 3 by 4, if I divide 3 divided by 4, so I can get that I1p upon I1q which equal to I2 times r upon I2 times s. Now I1 values and I2 values gets cancels. So if we can cut that I1 I2 and I1 I2, so we will end up a simple expression P by Q equal to R by S. Now here you can understand what is the use of my known resistance. So this simple expression we will reach. So this is the state of balanced condition. So P by Q equal to R by S. So this proves the condition for the balanced Wheatstone's bridge. So this condition only reaches when the galvanometer shows no deflection in the circuit. That is in the balanced state. Now when the bridge is balanced, it means through the galvanometer current flowing through the galvanometer is 0, then we can able to get that ratios of resistance. Now whatever the resistance values we have taken, so those resistance ratios, now here we can easily find the value of unknown resistance. Suppose if I know the P equal to R equal to S equal to 1 mega ohm. By using Wheatstone's bridge, I need to find the value of Q. Q equal to how much? So what all we need to do is that we need to bring the Wheatstone's bridge circuit in a balanced state. So how we can get that balanced state? By rearranging these resistance values. So if I able to rearrange these resistance values, P by Q is equal to R by S. So if I can substitute all these values in the above expression, so this will be changes as P is 1 mega ohm and Q I need to find, which equal to R is also 1 mega ohm and S is also 1 mega ohm. So this left hand side gets cancelled. Therefore 1 mega ohm upon Q, which equal to 1. Therefore Q equal to 1 mega ohm. So to reach the balanced state, we need to arrange these resistance values are equal. So if you can able to do that, the known resistance values or matches are equal, then the bridge reaches to balanced state. When bridge reaches to balanced state, the Wheatstone's bridge reaches balanced state, then easy to find the unknown resistance value. So this is the greatest application of the Kirchhoff rules to find the unknown resistance value by connecting them such a way like that in Wheatstone's bridge pattern. So Wheatstone's bridge contains 5 resistors. So here galvanometer resistance is also we need to consider as one of the resistance. So Wheatstone's bridge contains 5 resistance. So it contains 5 resistance and 4 resistance are connected in that particular arms, and 5th resistance we connected across the bridge B to D, and the EMF we need to apply across the ends A to C. So it contains 5 resistors. So in that G is also galvanometer resistors. So in balanced state, so what happens in balanced state? 2 things happens, that is the ratios of resistance are equal. P by Q equal to R upon S. Or if you can do the cross multiplication, this also you can write as P by R equal to Q by S. Anything is possible because it is equal. You can exchange the denominators to numerators. So in balanced state, the ratios of resistance gets equal, and not only that, at the balanced state, the current through galvanometer becomes 0. So when these things happens, the current through galvanometer becomes 0, the ratios of resistance are equal. Or vice versa, when ratios of resistance are equal, then current through galvanometer equal to 0. So this can be more handy when we deal with practical. So in the practical we used to do that. So when bridge reaches to balanced state, so the galvanometer, it do not show any deflection. So that we can understand while doing in the practical. But theoretically you can understand that the condition for the Wheatstone's bridge is that the ratios of resistance are equal when the bridge is balanced. So in that case, the current through galvanometer resistance equal to 0. So this is all about applications of Kirchhoff laws under the concept of Wheatstone's bridge.